Welcome to Physics Can Be Fun with me, Stephen Thomas. We've just been swinging this little keyboard around. We stuck it down on middle C with a piece of chalk and a rubber band. Now that's almost as irritating as a mosquito. And we all know with a mosquito we hear that eeeeong, and ask the learners when we hear eeeeong, they know that the ew means it's flying past you, missed you, it's chosen someone next to you to bite. And they all know the sound of a car coming towards us goes ew, and the woo. We've got to explain that there's a difference between the change in frequency and the change in the level of the sound. It's not only that the sound gets softer and fainter as it moves away from us, it also changes frequency. Now this apparent change of frequency as a source and a listener move together or apart is called Doppler. It's an apparent change of frequency. And the listener, which is you, or the computer if it's recording it, records an actual change in frequency. And the lovely thing about Doppler is there's really only this formula, and this formula. So there's only three very simple formulae. So let's imagine that I'd spent some time, thought up this little experiment that I'm going to take a piece of string. There's the keyboard, and we swing it around. Let's suppose that this is going in this direction. So we are swinging it, and every period, every small section of a second, this little keyboard vibrates. Now I've stuck it on middle C. We looked that up. It's 262 hertz. So 262 times a second, something vibrates producing that tone. And 262 times a second, you find that a little circle or ripple of sound ripples out from the vibrating object, which in this case is the speaker of the keyboard. But when it's moving, as we're swinging this around, because the source is moving, the ripples are, as this moves forward, we get these circular ripples formed, but every time this is moving closer to this side, so it squashes the ripples together, increasing the frequency as it approaches. Let's suppose here's my ear, or let's suppose it's a microphone of the computer. The ripples are squashed together on the side where it's coming towards us and spread apart on the side going away from us. So as this comes past here, we're going to hear ew. So here is the low frequency, here is the high frequency, and the frequency and the wavelength are inversely proportional, as we see from this formula. So the greater the frequency, the shorter the wavelength or the distance between the ripples. And here, low frequency, high wavelength or long wavelength. Now, let's do a classical Doppler problem. So where do we start with all problems? We write down the values that we're given. So we've got the frequency of the source. Frequency of the source is middle C, which is equal to 262 hertz. The frequency of the listener we're trying to figure out. So let's put a question mark there. The velocity of sound in air is approximately, let's say, 340 meters per second. They will give it to us. What else do we need? The velocity of the listener. Well, the listener's not moving. The computer or my ear is not moving, so the velocity of the listener is naught, and the velocity of the source. Now, how fast was this moving? And this is where, instead of just spending time giving notes, we get the learners to use some of their mathematical knowledge to figure out how fast was this keyboard being swung around. Now we could drop a source of sound. We could have dropped the keyboard past the computer, and using our equations of motions we could work out how fast it's moving, but get them to work out how fast. Now what we could do is we could say, if you listen to that again, you'll hear it goes and 1 and 2 and 3 and 4. So in other words, it's going around and 1 and 2. It's doing one full circle in 1 second. And the length of our rope was 1 meter. So what is the circumference if the radius is 1 meter? And this is where we can put our maths into effect, that if you take pi times diameter, 2 radiuses, pi times diameter gives you the circumference of the circle. So the circumference of the circle is pi times diameter, where pi is 3,141. So pi times 2 radiuses, or pi times diameter, where the radius is 1, comes to 6,283 meters, and it's traveling that 6,283 meters in 1 second. So let's put our velocity of the source is 6,283 meters per second. So there we've got everything we need to work out when it's coming towards us and when it's moving away. So why don't we work it out for when it's coming towards us? Now we know the frequency is going to be higher. So we can look at this formula. If we're teaching it, we first teach what all of these values stand for in a practical example. There is a plus and and minus here. That's the only thing that can be a bit tricky. So there's a mnemonic, or a way that we can remember, is it plus on top or minus on top? Well, if something is coming towards, we remember a T is simply a plus and a minus. So if it's towards us, we use this formula with plus on top and minus on the bottom. There's the T, to, which stands for towards. It's got a plus on top and a minus at the bottom. So there becomes our formula when it is towards us. So let's get rid of this and let's solve the problem when it's coming towards us. So we write it out, frequency of the listener equals, now this is just going to be a little bit more than 1 or a little bit less than 1. If it's towards us, whatever is in brackets must come to more than 1. So times frequency of the source, what is this? V plus, because it's towards V listener, V minus V source. So we're trying to find out the frequency of the listener is equal to 340 over 340 plus velocity of the listener, 0, minus velocity of the source, 6,283 times frequency of the source. Well, what is the frequency of the source? 262. Now we know that that is going to come to a little bit more than 1. So let's see how much this fraction comes to. 340 divided by, open brackets, 340 minus 6.283, close brackets, and that gives us 1,02 or 1,0188. So it's important when we teach this to tell that this is just a little thing that fractions it up or down. So inside this brackets we've got 1,0188 times 262, and that gives us 266,93 hertz. So from middle C, which was 262, we subtract that from that and we see that it comes to 4,93. So that's the difference. It's gone up by 4,93 hertz. And so we could also do the same for when it is going away from us. When it's going away, all of this will be the same. Let's just leave those values in, change that to minus and plus, and let's just work that out to see what the answer when this would be towards us. What would it be when it's away from us? So it's 340 divided by, open brackets, 340 plus 6.283, close brackets. Now here the fraction comes to 0,981. Do you see that all of that stuff in brackets is just going to make it a little bit more or less than 1? When it's moving away from us, less than 1, times 262. So times 262 equals 257,25 hertz. 257,25 hertz. So there's higher frequency when it's towards us, lower frequency when it's away from us, and there when it's right next to us or it's not moving at all, we hear middle C. So how nice is Doppler?